often hear that data cleaning is essential for good analysis. But what if the very act of cleaning your data introduces new problems? Today, we'll explore why so-called clean data can actually be dirty, and how common practices like deletion and mean imputation can distort your results. By the end, you'll understand why cleaning is not just a technical step, but a critical modeling decision that can change your findings in subtle but important ways. Cleaning data isn't just about making your spreadsheet look tidy. Every decision you make, what to delete, what to fill in, can alter the estimand, the sampling mechanism, and the bias-variance trade-off in your analysis. This means that cleaning is a modeling choice, not just a technical one. Understanding the statistical dangers behind these choices is crucial for drawing valid conclusions from your data. Frequent intuitive error is to simply delete rows with missing values. Imagine you have 1,000 survey responses, but 100 are missing income data. Many analysts drop those 100 rows thinking they now have a clean dataset. But what if those missing values aren't random? If high earners are less likely to report their income, deleting those rows changes the observed distribution and introduces bias into your results. When you delete rows with missing data, you might be quietly changing the story your data tells. For example, if high earners are less likely to report income, your clean dataset will underestimate average income. The expected value of income among observed cases is no longer the same as the true population mean. This subtle shift can lead to misleading conclusions, all because of a seemingly simple cleaning step. Understand missing data. Statisticians use the R indicator. For each data point, R equals 1 if it's observed and if it's missing. The central question is, what does the missingness depend on? Is it related to observed values, missing values, or something else? This distinction is crucial for choosing the right method to handle missing data. First mechanism is MCAR, or missing completely at random. Here, the probability that data is missing does not depend on either observed or missing values. For example, if a lab tray is accidentally dropped and some samples are lost, the missingness is unrelated to patient characteristics. In this case, deleting missing data doesn't introduce bias, but it does reduce your sample size and statistical power. While deletion under MCAR is unbiased, it comes at a cost: reduced precision. With fewer data points, your estimates become less reliable and your study loses statistical power. This means you're more likely to miss real effects simply because your sample is smaller. Even when deletion is safe, it's not always ideal. Second mechanism is MAR, or missing at random. Here, missingness may depend on observed data but not on the missing value itself after conditioning. For example, income might be more likely missing among younger respondents, but among people of the same age, missingness doesn't depend on income. In this scenario, deletion can introduce bias, so more principled methods are needed. When data is MAR, deletion is risky because the missingness is related to observed variables. Instead, statisticians use methods like multiple imputation, inverse probability weighting, or likelihood-based approaches. These techniques account for the missingness mechanism and help recover unbiased estimates provided the assumptions hold. Third mechanism is MNAR, or missing not at random. In this case, missingness depends on the missing value itself, even after accounting for observed data. For example, people with very high debt may be less likely to answer debt questions. Standard methods like deletion or mean imputation can be biased under MNAR, making analysis much more challenging. When data is MNAR, you need more advanced strategies. Standard deletion or imputation won't work. Instead, analysts may use external information, sensitivity analyses, or specialized models like selection models or pattern mixture models. These approaches help assess how robust your findings are to different assumptions about the missing data. Common quick fix for missing data is to replace missing values with the mean of observed values. While this seems reasonable, it can seriously distort your analysis. Mean imputation reduces the variability in your data, making your results look more precise than they really are. This can lead to overconfident conclusions and inflated significance. When you use mean imputation, every imputed value is exactly the same. This pushes the sample variance downward because those points don't contribute to the spread of your data. As a result, standard errors become too small and p-values can become falsely significant. This is a classic case of the analysis being misled by a seemingly simple fix. Mean imputation doesn't just affect variance, it also distorts relationships between variables. For example, if you impute missing y values with the mean, the imputed points form a horizontal band. This shrinks the covariance between x and y, causing the estimated slope and regression to attenuate towards zero. In other words, you lose the true relationship in your data. Multiple imputation is a principled approach for handling missing data under MAR. Instead of filling in a single value, it creates several completed datasets using stochastic imputation. Each dataset is analyzed separately, and the results are pooled to account for uncertainty. This method preserves variability and relationships in the data, leading to more reliable inferences. Another robust method is inverse probability weighting, IPW. Here, you model the probability that each data point is observed, then reweight the observed cases to recover population estimates. This approach is especially useful when the outcome model is complex, but predictors of missingness are well measured. IPW helps correct for bias introduced by non-random missingness. With multiple imputation, you don't just analyze one completed dataset. Instead, you analyze each imputed dataset separately and then pool the results using Rubin's rules. This process combines within dataset and between dataset variability, giving you more accurate standard errors and confidence intervals. It's a powerful way to reflect the true uncertainty in your analysis. Handling missing data responsibly means following a clear workflow. First, describe the missingness, which variables are affected, how much is missing, and whether there are patterns by covariates or time. Next, hypothesize the missingness mechanism, MCAR, MAR, or MNAR using domain knowledge. Then match your method to the mechanism, and finally report your assumptions and diagnostics transparently. Good rule of thumb: if you can't confidently defend the MCAR assumption, treat deletion and mean imputation as high-risk defaults. These methods are only safe when missingness is truly random. Otherwise, they can introduce bias and undermine your analysis. Always consider more robust alternatives when in doubt. For those interested in diving deeper, several classic references can guide your understanding of missing data. Key works include Rubin's Inference and Missing Data, Little and Rubin's Statistical Analysis with Missing Data, Van Buren's Flexible Imputation of Missing Data, and Ender's Applied Missing Data Analysis. These texts provide both theoretical foundations and practical advice. Summary: cleaning data is more than a technical chore, it's a modeling decision with real consequences. Deletion and mean imputation can introduce bias and distort your findings if not used carefully. By understanding the mechanisms of missingness and choosing principled methods, you can ensure your analysis remains rigorous and trustworthy. Clean responsibly and let your data tell the true story.